Hello everyone, welcome to COMP3141. This is lecture 4, video lecture 4 I believe, which is about how we can develop property-based testing properties or properties that we wish to prove, and how we can actually come up with those in the first place. So previously, in previous videos and in Curtis's lectures, you would have seen how we can prove properties. That was in week 1 and 2, and then how we can test properties using quick check and property-based testing. But in all of those examples that we've shown you so far, the properties that we tested or proved, we came up with and just told you. But how do we actually come up with the right properties to test or prove in the first place? What sort of methodology can we apply in order to make sure that the properties that we test or prove actually constitute a functional correctness specification? So we're going to look at a few different types of properties today, and we'll see how they relate and how they constitute a definition of correctness. So firstly, we need to talk a little bit about how we structure programs in Haskell and indeed in any other programming language. So typically, a Haskell program is made up of many modules, right? And a module exports some data types, some types that we define. And then, in addition to those types, we'll also have some functions, which we call operations, on those data types. So there's a few different formats that this can take, but typically we'll have a function to construct a data type, which may or may not be the actual data constructor for the data type. We'll see examples where that is the case today, and we'll also see examples where it's not. And we'll also have functions that query information from the data type, so they will take in as an argument some type X, which is our data type, and produce some results, right? They'll give us some information. And then also we'll have functions that update the data type. And it depends on your language as to how these look, but in Haskell, these will typically both take in and produce a value of type X, because we don't have destructive updates in Haskell. Instead, we just create a new data structure with some changes made. So typically, most software is designed with this structure. Even if you're used to object-oriented programming languages, typically in those languages, each module is effectively a class, and you have a constructor for the class, you have methods that produce information from that class, and then you have functions that act and update the data inside the class. So this scheme even applies to object-oriented programming. But let's look at how it can be done in Haskell. So I'm going to define a module in Haskell for a dictionary. And it's just like an English dictionary. We're going to have words that we can look up and definitions associated with each of the words. So I will go over to my terminal here and load up dictionary.hs. It's going to give me errors because I haven't implemented anything. But for a dictionary, we're going to need a few ingredients, right? We need a constructor, which is our empty dictionary. And it doesn't take any arguments, so it's just a constant dictionary. And I'll leave that comment for later. We have an insert word function, which, given a word and a definition, which we just defined to be strings, we'll take in a dictionary and return a dictionary. So this is an example of an update function. And then we have a function lookup, which is like a query function, which, given a word and a dictionary, produces maybe a definition, if there is one in the dictionary. So let's implement this. And we'll just start by implementing it in a very simple way. So I'm going to create a definition here for this dict type. So I will say it has a constructor called D, and inside it is a list of dictionary entries, right? And what is a dictionary entry? Well, let's say that let's make our own type for that. And in fact, I've defined one already, so I'll just copy paste it because it makes it a bit easier. But this is a record, and inside this record we have a word and a definition, right? Now, of course, you can define this just using a tuple of a word and a definition yourself, but using a bespoke type like this gives us these accessor functions that are a bit more informative than just first and second, so we can have word and definition instead. So it's a little nicer. So we'll be using this dictionary entry type, and our dictionary is just a sequence of these, a list of these. So now we can implement this dictionary data type. We'll say the empty dictionary is a dictionary that contains no entries, right? So it's just an empty list. And if I want to insert a word, W, with the definition D into a dictionary with these entries, then I just add a new entry with that word and definition onto my entries and return that in a dictionary. And then to look up, well, there's actually a function built into the prelude called lookup. I've hidden it here because I didn't want the term lookup to be overloaded. So, and the way lookup works, if I look at the type of the prelude lookup, the default lookup, it would give me the type like this. Lookup is of type list of tuples of A and B to A to maybe B. I believe that's right. In fact, we can double check. Type of lookup. Oh, it's the other way around. So it's actually EQ of A, like that. So it takes the element first and then the list. So our lookup function for a dictionary is actually quite similar to this. So we'll have a dictionary of entries, and we want to find the entry that corresponds to the word W. So what I'm going to do for now, this will not be the final version of this data type, but for now I'm just going to be cheap, and I'll say prelude.lookup, so I'm going to refer to the original lookup function. I'm going to look up the word W, but the listed it once is not in the same format as ease, because ease is a list of dictionary entries and it expects a list of tuples. So I'll just quickly convert these dictionary entries, entry with the word and definition, to a tuple of the word and the definition, and then I'll apply that to my list ease, and then I'll look it up with the prelude lookup function. So this is a very cheap way to do it. Basically, what the prelude lookup function does, you can tell from the EQ here, is it just looks through this list until it finds an element that satisfies equality with this given element and returns the B that corresponds to that. So that does exactly what we want here. So I just converted my list of dictionary entries into a list of tuples. Now you might think, oh, what if our dictionary entry that we're looking for is the very first thing in the list? And then we would have spent all this effort converting all of these entries when we only wanted the first one. Well, that would be the case if Haskell were not lazily evaluated. But because Haskell is lazily evaluated, that means that each of these conversions on the elements only happens when we actually need that particular element. So it will not convert the entire list to tuples and then look it up. It will convert as it goes, looking it up. So if we find the definition we're looking for, it won't convert any further parts of the list. So lazy evaluation can be a helpful optimization in many cases. Okay, so here's our implementation of a dictionary. So I will just say that the dictionary should derive show so that I can see it, so I can look at it. Maybe EQ might need that as well, so let's just add that in as well. So now if I go to my terminal, it doesn't like that. Oh. All right, I need to do this. And then I can do that. Right, I think that's going to work now. There we are. And I just used the wrong constructor here normally students would shout out that they see a typo, but I don't have that luxury anymore. So I don't notice the typos until GHC points them out. But now I can insert a word. The word is COMP3141, and the definition is a good course. And we'll put that into the empty dictionary. And we should get the dictionary that contains that definition. And now I can look up COMP3141 in this dictionary, and I get my definition back. So it seems to be working just fine. Okay, now the problem with this is it's a little bit inefficient. For example, we have no real ordering of these dictionary entries. The dictionary entries are not sorted in alphabetical order or anything. So, for example, there's no way to tell that the word we're looking for is not in the dictionary without looking through the entire dictionary. We can't early exit from our loop because we're already confident that the word isn't there. So it would be nice if the dictionary is in sorted order, then you can do something like you do with a real dictionary, which is the moment you see that if you start at the beginning of the dictionary and you work your way through, if you see a word that occurs after the word you're looking for in the alphabet, then you know that you won't find the word you're looking for. So we could early exit from the loop there. Furthermore, if the dictionary was in sorted order, we could also do binary search, but because Haskell's lists are singly linked, binary search isn't the advantageous algorithm that it is on arrays. So we'll just try and do the early exit approach. But before we do that, I'm going to discuss a little bit about how we make sure that this is something we can maintain. So there's these things called data invariants. So data invariants are just properties that pertain to a particular data type, and they constitute the definition of well-formedness. So the idea is it's an invariant, which means it should never change. It should always be true. So when we construct the data type, it should be true then. And then every operation we do on our data type, whenever we change our data type, it should maintain that invariant. So the invariant should never become falsified by our operations. And then if we query information from that data type, if the queries can make these assumptions that the data invariants are true whenever they look at the data structure. So an example would be that if our dictionary was always in sorted order, that property should be maintained across all of the operations of our data type. Binary search trees should satisfy the binary search tree properties, or even something like a date value should never be invalid. You can't have 31st of the 13th, 2019, which is last year because I forgot to update these slides. That's not a real date. So if you can have data invariants that talk about validity of data as well. So well-formedness predicates, these notion of data invariants, are encapsulated as what's called a well-formedness predicate. And you just need to show that that well-formedness predicate is maintained across all of your operations. So the way that looks is we have this function, which we'll call well-formed, right? And it's a well-formed defined on our data type. So in this case, it might be a dictionary, and it'll return a Boolean. And it will return true only if our data invariants are maintained or hold for that particular value that it's given. And the idea is essentially every input value of type X satisfies WF, then all the output values should satisfy WF. So that's the property that we want to construct. So I will demonstrate this with the dictionary example. Let's go back to there. So the property that we want to say, the well-formedness property for our dictionary, is that the dictionary with its entries is sorted, right? And what do we mean by sorted is? Well, I'm just going to derive ORD here because, well, actually we don't need to derive ORD. we're actually only interested in the words being sorted. Their definitions, if they've got the two of the same word, then their definitions do not have to be in sorted order. So let's try that. Let's go sorted. So we've defined this sort of predicate before, but let's just do it again to make sure that we know what we're doing. So if I have a dictionary, oh wait, no, we're talking about a list of A's, or a list of dictionary entries to bool. If I have no elements, that's going to be true, right? The empty list is always sorted. If I have one element, that's true too. And if I have two elements or more, then if the first element, the word of the first one, is less than or equal to the word of the second one, then it's still in order as far as we know, so long as the rest of the list is in order. And otherwise, it's not sorted. So that's our definition of sorted. And you can write this a few different ways, but this is how I chose to write it this time. And now what our properties will be for our dictionaries is that this data invariant should be maintained across all of our operations. So the first one is that the constructors establish the invariant. So the empty dict should be well formed. And then we can do lookup as well. So let's do that. Lookup is well formed, says that if I have a word and a dictionary, then, well, actually, there isn't much to say here. We can assume that the dictionary is sorted inside lookup to optimize our implementation, and we will do that. But there's no property to test that lookup maintains the well-formedness predicate, because lookup doesn't update the dictionary. So if the dictionary previously satisfied the well-formedness predicate, it still will after we look it up. So we only need one other property here, and that's for insert word. And morally, the way it looks is we'll have the word and the definition and the dictionary, and we'll say if the dictionary is well formed, then we will insert the word W with the definition D into the dictionary, and then after we've inserted it, it should still be well formed. Right? So that's the definition. But if we did that, then this property would not be very friendly to QuickCheck. We've previously discussed this problem. Essentially, what QuickCheck will do once we implement arbitrary for dictionary is if we just picked any arbitrary dictionary, the chances of it being well formed, the chances of the dictionary entries being sorted is pretty low. So if we have this requirement that the dictionary is well formed, and we just generate any arbitrary dictionary, the chances of this predicate being satisfied is pretty low, and therefore it will discard a lot of test cases and ultimately give up. So the way to fix this is to make sure that when we generate our dictionaries, we only generate well-formed dictionaries. And then, whether or not you leave this predicate in or not doesn't make a difference, this precondition. If you have the precondition, well, it's always going to be true, so it'll keep working. But if you remove it, well, your generator better generate well-formed dictionaries, and that's all there is to it. So I'm going to leave it in just to make sure that it's our generator works correctly, and that way if our generator does generate any non-well-formed dictionaries, it will just discard those tests. So exactly how to implement generators we haven't taught you yet, and I won't be teaching you in this lecture either. We might look at it a bit next week, or otherwise after the break in week 7. Week 7, yes. So I'm just going to grab some of the code that I have written previously and then we don't need the definition of dict because we already have that. You don't really need to understand how this instance works. Essentially what this is doing is for the entries, for the arbitrary dictionary entries, it just generates two arbitrary strings, an arbitrary word and an arbitrary definition, and then chucks them in. And for the dictionary, it generates an ordered list of arbitrary things. But in order to use this ordered list modifier, which we've seen in the last lecture, we need an odd instance for dictionary entries. So I will copy this, but essentially the odd instance for the dictionary entries is essentially what we're doing with our sorted definition here. It's just comparing the words. It doesn't bother comparing the definitions. So that means we can actually take a more general version of sorted here that just takes any A that is of instance, an instance of type class odd, and then I don't need the word function here. And now this sorted predicate, if we ever needed it for anything else, it would be very easy to use for any other instance of odd. And this is exactly the same code, essentially. It's just using this type class, and this type class is what does the actual comparison. Okay, pardon me. So we have our arbitrary instance here, and once again, don't worry about this code. If it's not clear to you what that does or what these symbols mean, we'll be talking about that later in the course. But suffice to say, this is generating an ordered list of dictionary entries, and that's exactly what we want. So now we have our properties that check the data invariant is maintained, and now we want to see if that data invariant is in fact maintained. Now, looking at this code, you probably think, well, none of this depends on the ordering being sorted, and in fact, insert word looks a little suspicious, but let's see if quick check can find it for us. Oh, it doesn't like that because I forgot to import test.quickcheck. Okay, did I make a mistake, or is it lowercase c? Hold on, maybe my setup doesn't have quick check. Oh, I think it's because I upgraded GHC, so everything is fresh. Okay, so I have finally finished building quick check. So now, hopefully, when I start my REPL and I load my dictionary.hs. Okay, now I just need to fix this typo and load it again. It's all good. Okay, so now we can actually run quick check prop. Well, let's do empty dict first. That one's easy. There's only one test to run because there's nothing to generate. Now let's try insert word. Doesn't work. And the reason it doesn't work is because if when we insert into our dictionary, we are just inserting at the beginning. And we expect it to work by inserting into sorted order. And in addition, our lookup function also doesn't seem to care whether or not the order is maintained. So we should actually make this order sensitive. So the way to do this is we need to insert into sorted order. So what I'll do is I'll write a helper function that is insert sorted the entry WD into our entries. Okay, and where insert sorted takes any ordered a thing and a list of those things and just inserts them into the list. Now I believe this function is actually in the standard library, but it's always good to implement it for practice. So we've got our entry, we've got the empty list. In that case, we just return that entry in the list. And otherwise, if we have an entry and there's x followed by x's here, then if our entry is less than or equal to x, then we'll say x's, because x is bigger, so it can go after. And otherwise, we don't need to rewrite the equation, we can just go otherwise. We will put x first and then insert sorted ex's, and these parentheses are not needed, so that's all the same thing. Okay, so there's our insert sorted function. This is probably in the standard library, but I thought it would be nice to implement it. So now we have insert word, and hopefully this insert word satisfies our tests. Indeed, it does seem to. So now the next thing is we want our lookup function to to be more efficient, to be able to do this early exit. So what we'd want is to have a different lookup function, lookup sorted, and I'm not going to convert the entries because we can just write this function on entries directly. So we have lookup sorted, it's going to take in a word and a list of entries. Oh, did I call it dict entry? Yeah, dict entry, and return a definition for us, maybe, if it can find one. So now, lookup sorted, the word w, if we have run out of entries, then that means we can't find the definition. If we have an entry here, and followed by possibly more, then if the word, let's compare the word, or let's just compare the word of E and W, right? So depending on whether W is less, greater than, or equal to, we will do different things. So I'm going to use a case of statement here, and I know we haven't seen these very often, but essentially this is just matching on the output of the compare function. And if you remember, compare returns three possibilities, LT, EQ, and GT, which is an ordering, right? That's a data type that's built into the standard library. So we have these three constructors here that we're matching on. And in this case, LT means that W, the word that we are looking for, is less than the word at the front of the dictionary that we're looking at. This means that the word can't be there because the word we're up to in the dictionary is bigger than the word that we're looking for. So that means it's nothing. If it's equal, then we've found the word that we're looking for, so we'll just return the definition in the entry that we found. It's called definition, right? Let me just double check that. It's defin. Okay. Now we have, if it's greater, then we've got to keep looking in the dictionary. So we will look up sorted WEs. Oh, and this should be just because we are returning a maybe here. Okay, so there's our lookup sorted. And if we're not confident that this is correct, we don't have any quick check properties yet that test the test the lookup function. So what we can do is call our old lookup function that we are more confident is correct, the lookup prime function, and we can just go prop lookup prime, right? The thing that relates these two, word dictionary equals, and then we just say lookup, the word in the dictionary is equal to lookup prime, the word in the dictionary. And that way it should work regardless. And let's see if that works when we try quick check. Now I actually know it won't, but let's see. Oh. Eventually it should not work. Okay, so this is an interesting example. Oh, I know why it's working. Because our arbitrary dictionary instance is producing well-formed dictionary entries. If we didn't know that the dictionary is well-formed, we would have to add a precondition like this. And that's why I was expecting it to fail, because we didn't have that precondition. But of course, because our arbitrary instance always generates well-formed dictionaries, this does actually work. Okay, cool. So now we have a complete set of properties. So our lookup function is now more efficient, and we have an insert function that hopefully passes tests. It certainly does. So now we have the efficient implementation of a dictionary, and we also have some quick check properties that assert that the data invariants for that dictionary entry that's sorted are maintained. Good. So going back to the slides now. Where's my thingy? Here it is. The next thing we need to worry about is we've proven or established, at least with tests, that these well-formedness predicates are maintained by the operations that we just tested. So we know that it's safe to use empty dict and insert into dict and lookup. But that doesn't stop another programmer from coming in and writing their own functions on dictionaries and messing up everything that we just worked so hard to establish. Instead of using insert, they could just write their own insert function that inserts it in the wrong order. And so what we want to do is prevent this kind of thing from happening. We want to make it impossible for another programmer, either maliciously or by accident, to access the parts of our data type that could violate the invariants and thereby break them, right? And the way we do that is to restrict the interface of the data type to only the operations that we define. So we define some operations, like insert and so on, and then we make sure that the only operations that any programmer can use is those operations. We do this with what's called an abstract data type. So you've heard of abstract data types before, I hope, when you did C, but it has nothing to do with pointers, it has nothing to do with header files. All it is a data type where the implementation details are abstracted. And what does abstract mean? Well, if you're familiar with abstract art, it just means the removal of detail. Instead of expressing every detail about everything, you just extract from that the essence of the thing, and you display that in abstract art. And an abstract data type is actually kind of similar. Instead of worrying about how the dictionary is implemented from the perspective of anyone else except for the implementer, the abstract data type is just a thing. We have this mental model of what's going on, but we don't really care or know how it's implemented. So we associate some operations to the data type, and we just present those operations, and we do not present how they're implemented. And that's an abstract data type. So the way we prevent programmers from having access to the implementation details of a dictionary, for example, is to use modules. So let me show you how to do that in Haskell. So there are other programming languages where you do this in other ways. When you did it in C, you used a header file. But here we just go module. So we type the name of the module that we're defining. And this one is called dictionary. And it exports the following things. So we put this parenthesized group here, and inside we say these are the things that you'll be able to use when you import this dictionary module. You'll be able to use the word type that I defined and definition as well, which are just type synonyms for string. You'll be able to use dict, that dict type, and then you'll be able to use the operations empty dict, insert word, and lookup. Now note here that I didn't include anything else, right? So none of these helper functions or properties or anything like that. And this is all we have in our interface. And in particular, the constructor D here, this constructor is not exported, which means when I import dictionary, I can use dict, but the only way I can use dict is with these three functions: empty dict, insert word, and lookup. We can't use them. We can't just pattern match on the dictionary and extract the list of entries inside. The type dict entry is entirely internal, so it's impossible to use that type as well. All of that is internal to the module and is not exported out. It's abstracted away from. And so this means that the only place where our data invariance could be violated is in this module. It's impossible for anyone else to violate a data invariance. And because we just tested these three functions that we defined in this module to satisfy our data invariance, that means that our data invariance can never be violated, right? So we've sort of established that our data invariance are inviolable, and we did this using abstraction. So there are some programming languages where this is not really well supported, like Python, and this is one of the reasons why you don't use Python for real programming. Or at least you don't use Python for real programming when you care about things like assurance. Okay, so we just made an example of an abstract data type that maintains our data invariance. And to give you a bit more background here, this notion of abstraction is actually probably one of the most powerful tools that we have in terms of formal methods. Abstraction doesn't solve all our problems. We'll talk a bit about that in a moment, but essentially abstraction is the main tool that we use to be able to construct mathematical properties about complicated systems. So abstraction is just this process of eliminating detail. It doesn't have any runtime penalty. So some people say that, oh, if you have a lot of abstraction in your program, then it's going to be slow. But that just makes no sense. A lot of people think that because of object-oriented programming, I think. I'm not sure exactly. But it has nothing to do with runtime performance. It's entirely about just this process of eliminating the detail and just programming towards a mental model of how things are going. So we don't reason about our dictionary after we've implemented it in terms of a sorted list or however else it's implemented. It could be implemented using some weird tree data structure. It doesn't matter to us. When we reason about a dictionary, we just have a mental model of a book that we look through and we find definitions in. And we don't care exactly how this is represented on a computer. So it's abstract in that sense. The opposite of abstraction is called refinement. And we'll be seeing some uses of that term in the next section. Okay, so another use case for these modules and for data invariance is for data validation. So I showed you before this example of a data invariant that says this date is a valid date. And we can do a similar thing with stuff like email, right? So suppose I have this email function. Now this IO thing, we'll be talking about this actually a bit more in 1 week, that should say. We'll be talking about it next week. But for now, you can just think of it as an action or an imperative program that actually is going to send an email, right? So given a string, which is the email address, and a message to send, this function will just send an email. Now, the first problem you should notice is as soon as you see string to IO, that's kind of bad because there's no way to tell which of the two strings is the email address just from looking at the type signature. There's a comment here, which is good, but maybe this is just version 1 of the software, and in version 2, the arguments are swapped around, but someone forgot to update the comment. This happens all the time, and there's no way to tell just by looking at the type. So we probably want to change this function somewhat. So suppose I wanted to make it impossible to call send email without first validating that email to check that it was a valid email address. So there's a lot of complicated ways to check if an email address is valid, but at least you can say that all email addresses need to have an @ sign in them. So let's assume that we're just going to check, you have to check that the email address has an @ sign in it before you're allowed to call send email. So what we can do is actually enforce this and make sure that the programmer must check that their email address is valid before they send an email with this send email function. It's not just a convention. We can actually make the compiler enforce this for us. And the way we do this is with abstract data types. So what we'll do is we'll create an abstract data type for a valid email address. And so it's an abstract data type with a type, which is email, and it'll have a constructor. And that constructor will make sure that our data invariant is maintained. And then whenever we want to send an email, we have to use this email abstract data type. And because the only way to construct an email abstract data type will be to use our special safe constructor, that will guarantee that all emails that we send will be checked. And I'll show you how that looks. We have it like this. So I have my email ADT, and it has a type email, and I don't export the constructor here. If I wanted to export the constructor, I'd have to put a little bracket here and then write email again, right? So in our dictionary example, it would be, if I wanted to export the constructor, it's just called D. So I just write it like that. But I don't want to export my constructor. You can also write this if there's multiple constructors. You can just use ... to export all of them. But I don't want to export my constructors here because I want to check the email whenever I create one. So because this is the only function that's exported that creates an email, the only way I can ever have an email in my program is if I check it first, right? And so then if send emails type takes in an email instead of a string, A, we've gotten rid of the ambiguity of the two arguments because now one of them is obviously the email, and B, we've enforced that you must check your email address before you send it using the send email function. And this kind of technique is extremely powerful and extremely common, and it's what's called a smart constructor. Essentially, you use a special constructor that enforces data invariants by checking them first. And sometimes you can even reuse the checking code between your constructor and your quick check properties, and that's kind of nice. Okay, so earlier I said that we don't reason about abstract data types in terms of their implementation. We just have a mental model of what's going on. So how can we formalize that notion? Instead of having to prove things about the implementation of an abstract data type, like we've been doing, or test things about the implementation, what we want to do is have a mental model of what's going on, and we want to codify that mental model into some programming language code. So let's take another example of an ADT. Something like a queue. Oops. So we have a queue here, and it's got a bunch of operations: the empty queue, enqueue, front, dequeue, size, right? And front and dequeue just take the front element of the queue or remove the front element of the queue, and they're both partial. So if the queue is empty, it's allowed to crash. We'll just assume that's okay. Okay, and we could try to come up with properties like we did with reverse, for example, like reverse of reverse is the same as identity and stuff like that. So we could say, if I enqueue an element onto the empty queue and then I dequeue that element, I should just get back the empty queue, right? And that's true for a correct implementation of a queue, but it's very hard to capture everything we mean by queue just by writing a bunch of properties like this. This is not a functional correctness specification. We haven't specified exactly what it means for a queue to be correct. So this kind of property is not ideal. What we want to do instead is formalize our notion of our mental model and then relate our mental model with the queue implementation. I'll show you how that works. First, let's come up with a mental model for queues. If you think about what a queue is, it's essentially just like a list where the empty queue is the empty list, enqueue is like putting something on the end of the list, and front and dequeue are just looking at the first element of the list. And size is just the length of the list, right? So that would be a really cheap and really easy way to implement a queue. So let's just do that. So we've got this implementation here, right? Empty queue, and I just put an L on the end of all of these because this is the list version. So empty queue is just the empty list, enqueue just adds to the end, front is just head, dequeue is just tail, and size is length. So this is a very, very, very simple implementation, but because enqueue uses this append function, and we've seen the implementation of append already, it's a order n append, right? It's going to go through the entire left list in order to add the element onto the end. So this is unacceptable for our particular use case, right? We need a high performance queue. And this order n enqueue operation is no good. We can still make use of this list implementation, however. It's dead simple. It's trivial to see that this implementation is correct, right? There's literally no way this could go wrong. So if we make a better queue implementation, it should always give the same results as this dead simple one. So this dead simple implementation is essentially our mental model of the queue. So then how do we relate our mental model to the implementation? If we look at the literature on this, it says to define a relation, which is a predicate that takes two arguments, right, between the queue and our abstract implementation or our mental model, which is written like this, right? Our relation takes in our implementation of the queue and our list version and just returns a Boolean, right? Because it's a relation between two things. And so we say that the empty queue should be related to our list version of the empty queue. And if we have two related, if we have a fast queue and a list queue that are related, then the size function should return the same results for both the fast queue and the list queue. And if we enqueue onto the fast queue and the enqueue onto the list queue, they should return related results if the original queues were related, right? So these three properties essentially say that our refinement relation, this special relation here, is preserved across all of the executions of the program. And I have this in pictures as well. Okay, sorry, there was a minor technical issue. I realized I was using the condensed version of these slides instead of the normal one, but it didn't really affect much. So if we want to see a pictorial representation of how these relations work, we can imagine that our program is just a sequence of these operations, right? So our data type module is going to be used by first creating an empty queue, and then some sequence of operations will happen to our queue after that. So this is like the lifetime of our queue. So it starts out being created as an empty queue, and then stuff might be enqueued and dequeued and so on after that. And we know from our property relating the empty queue that if we use the empty queue, that's the same as, or it's related to the empty queue in the list version, right? So we have established this relation between the empty queue and the list version's empty queue. And then we said that if we enqueue an element onto our fast queue, right, that's this black arrow, then if we enqueue an element onto the list queue, they're still related if they were related initially. So this blue relation carries over from the previous step. And then we enqueue again, and it carries over again. And then we dequeue, and we have a property for dequeue as well, and so on. So it's going to carry this relation through all the way through the possible lifetime of our queue, right? Because each of these properties ensures this relation is satisfied or is preserved, the relation will be preserved across the entire execution of the program. And if we ever use a query function, we have a property, say we use query function and we ask, what's the size of this queue here? It will return 0. And we have the query function tells us, the query function property tells us that because this and this, so the concrete empty queue and the abstract empty queue, the empty list, are related by our refinement relation, that tells us that they will return equal results, right? So rel of fq and lq implies that the size is equal for both. So that's why we have these three types of properties. And putting all of this together, this tells us that whenever we have one of these concrete queues, these efficient queue implementations, which we haven't implemented yet, mind you, but we will, then we can reason about it just as if it were a list of numbers, right? It's going to be more efficient than that, but as far as we're concerned in terms of correctness, it will behave just as if we were using a list of numbers. So whenever we use a queue, we can reason as if it were a list. That's the goal. So we could take our code here, and I think I will. Whoops, wrong way. Or maybe right way. Right way. So that was our dictionary implementation. That's all done. Now if I load my next example, the queue, it doesn't like that because I haven't implemented much. We have our abstract implementation here, which was from the previous slide. And we have our queue, which I haven't implemented yet, and each of the operations. So what I'm going to do first is specify each of these operations. So we have, so hold on. All right, so we have, firstly, we need to define our relation that relates our queues to our list of integers. Well, we can't define it yet because we haven't actually implemented queue, right? But we will eventually. So when we do, we will define rel. But in the meantime, we'll just leave it as if it were abstract as well. And then we go prop empty using the relation is the empty queue is the same as the empty queue L. And prop size R says that if I have fast queue and the list queue, then the fast queue and the list queue being related should imply that the size of the fast queue is equal to the size of the list queue. And if I enqueue using this, then fast queue, LQ, and I'm enqueuing an X element, then if my fast queue and LQ are related, then the NQ X, FQ, and NQ L, X, LQ should be related as well. Okay, so that's our three properties, but even if I just implement these trivially, or just put some undefines in here, we can already see that it's potentially not going to work well. And this is because of the same problem that we had with our data invariance. And that's because this rel fq lq precondition is easily violated by randomly generating the two queues, right? If I randomly generate a fast queue and I randomly generate a list of numbers, the chances of them representing the same thing are very low, right? If I randomly generate a list, it's probably 1, 2, 3, and then the queue is 3, 2, 1, right? Then they're not going to be the same. So the chances of them being the same is really, really slow, which means that it's going to discard almost all of the test cases if I use this refinement relation as is. So these properties aren't good enough for quick check. So how can we address that? Let me just skip over back to where we were. So it's very hard to satisfy these preconditions. So what we use instead is something called an abstraction function. So an abstraction function takes in a queue and produces the corresponding list rather than just taking in the queue and taking in the list and telling me yes or no if they're the same, right? So this will take in a queue and produce the corresponding list, and that's much easier to compute with quick check, right? So we'll actually define this toAbstract function, and then our refinement relation is essentially just saying take in the fast queue and the list queue, then the abstraction function applied to the fast queue should be equal to the list queue. But this actually lets us define our properties in a much more quick check friendly format. So let's do that. So instead of having the refinement relation, we're going to have toAbstract, right? And our refinement relation for the fast queue, list queue is just going to be that toAbstract of the fast queue equals the list queue. Pardon me. So toAbstract is going to take in our queue and give me a list of integers. And my queue is here. And I'm not going to implement it yet because we still don't have a queue implementation. But I'm going to use this to rephrase our properties. So now with the rel empty QL, we can actually rephrase that just by expanding the definition of rel, and we get to abstract of empty Q equals empty QL. And then for the size, we say rel of FQ LQ, well, that's the same thing as to abstract FQ equals LQ, and then size of FQ equals size of LQ. Now this is actually much more simplifiable, because if we know that LQ ought to be equal to this to abstract FQ, then we can just as easily not take it in as a parameter and just replace LQ with to abstract FQ. Right, so this is how I'm rewriting it, so I'm going to use the abstraction functions instead of using the refinement relation. So now here we also have FQ, LQ, and X. So this is the same thing as to abstract FQ equals LQ, which means that this is also to abstract NQX FQ equals this. So then how do we simplify this further? Well, we know that LQ is to abstract FQ, so I can not take that in as a parameter, and I just change LQ to abstract FQ, right? And so now if I look at my properties, they look kind of similar, but instead of using this refinement relation, I'm using this abstraction function. So it always ends up looking like this. Whenever you have an operation that updates the structure, it's going to be the abstraction function applied to the operation equals the operation applied to the abstraction function, right? So you have this kind of box diagram kind of layout. It's like a distribution function or something like that. So now that we've got this sort of pattern, we can do DQ as well. And this is almost exactly the same, except we don't generate an element to insert because we're not inserting anything. This is DQ like that. And now we can also do front. The front of a fast queue. So there we go, should be equal to, sorry, not to abstract, because front is a query function, it's not an update function. So front of the fast queue should equal front L of to abstract fast queue. And we did size, we did empty, we did NQ, we did DQ. I think that's all of them. So now we need to implement our queue functions. We've got all of our properties here. And to do this, I'll go back to the slides. We're going to use a kind of interesting implementation. So we're going to have a queue with 4 parts to it, or really 2 parts, and each part has a list and an integer. So there's going to be the front of the queue, which is the first list, and the size of that front, and then the rear of the queue, which is the second list, and the size of that. And the rear part will be stored in reverse order. This means if we're going to NQ something, we just add it to the front of our rear list here. Because it's in reverse order, that will be correct, right? Adding it to the front of the reversed rear is putting it at the back of the queue. And adding things to the front of lists, creating a new list node and just putting its tail to be the old list is order 1. So this should be order 1 complexity for NQ. So let's implement this queue function and this queue data type. So it's going to be the front and the size of the front and the rear and the size of the rear, right? So those are the 4 parts to it. The empty queue has an empty front, zero size front, empty and 0, right? So that one's not too bad. Now for our to abstract function, the rest of these I'm going to implement after we test our properties to do some test-driven development. So to abstract is going to take in our fast queue, which has a list of the front and the size of the front and the rear and the size of the rear, right? And it's just the front plus reverse of the rear, right? Because with the rear is stored in reverse order, so this is the list version of our queue. So that's our abstraction function. So now that I have that, it doesn't like it because I haven't implemented anything. Let's just keep going with the undefines. Okay. It still doesn't like it because line 8. Oh. Doesn't like that because it didn't have a type signature. Okay. Line 33, it says expected type Q got a list of integers. This should be size L. There we go. Maybe that's why it was giving me the other error too. Yeah, okay, it's fine now. Cool. So now we have all our properties. I can try and quick check some of them. We can quick check the empty Q one, which is called prop empty R, and seems to work. Of course, it's pretty hard to screw up empty Q, so let's try and do something a bit more interesting. Yes. Right. So the way we'll do that is we will have an element X, and we want to put it on the front or at the rear of our queue. Well, oops, we've got the front, the size of the front, the rear, the size of the rear. Then we're putting it on the rear of the queue, so the queue's front will be the same, and we'll just put it on the back. Okay. And then if we're getting the front, well, I'm only going to implement one of these cases, and we'll see why in a moment. But essentially, if we have an element on the front of our queue, and I ignore the rest, then I just return that element. And for DQ, we are going to do a similar thing, size of the front, rear, size of the rear, and we'll just remove that front element, so the size of the front goes down by 1. And note that I'm not dealing with the case where the front is empty and the rear has elements in it. And the reason for that is we'll be doing something about that using data invariance. So the size, the last function that we want to implement here is front, size of front, rear, size of rear. This one's easy because we can just say that the size of the front is the size of the queue is the size of the front plus the size of the rear. Okay, so these are our simple enough but a bit more complicated implementations. They're not done yet, but this is generally the spirit of what we're trying to do. But we're going to need some data invariance here. So if so hold on, I'll come back to this slide. So we need the data invariant. Firstly, the obvious ones are that the size of the front variable, the size of the front integer, should be equal to the length of the front list, and similarly for the rear. And also, we're going to have a third data invariant, which says that the size of the front is always greater than or equal to the size of the rear. So that means that if we're in our code here, when I DQ, if I see that the front is empty, that means the rear must also be empty. So that's why I can just deal with the case where the front has an element in it. Because I know that if the front is empty, then the rear is empty too, and we just won't have an element at all. But if the front has an element, then we can just DQ as normal. Okay? So that's why we're relying on the fact of the data invariant that says that the front is always at least as big as the rear. Okay. And we're going to have an arbitrary instance for our queues, which I am going to swipe from my comments. and I'm just going to put it in here, and we're going to have a well-formed predicate, right? Like we did before with the dictionary, we're going to have a well-formedness predicate for our Q, which is Q size of the front, front size of front, rear size of rear. So firstly, we're going to have the first data invariant, which is that the length of the front is equal to the size of the front. The second data invariant, length of the rear is equal to the size of the rear. And our third data invariant, which is that the size of the front, the size of the front is always greater than or equal to the size of the rear. Yep, that's right. Okay, so now we have our well-formedness predicate. Let's just write some properties. I think I have the names of them here. All right, so we'll grab those. So firstly, we need to show that our data invariant is established by our constructor, which is the empty Q. So well-formed empty Q. And then we need to show that NQ preserves our data invariant. So if I have an element and a Q, and I NQ the element onto the Q, if the Q was well formed, then the Q, oh sorry, it's not WF, it's well formed. Then the Q will be well formed again after I NQ. Now, our arbitrary instance here, you can sort of see what's going on. It's taking two non-negative integers and making sure that the vector of, like the two lists are of the correct size. So these arbitrary instance is actually generating two lists that are guaranteed to match our data invariance. So this well-formedness predicate will always be true, but it doesn't hurt to leave it in, right? So if we leave it in, that way we make sure that our arbitrary generator is doing the right thing. So we generate that, and now we do the same sort of thing for DQ. So DQ is much the same. We just DQ an element, and I think that's actually all. Yes, this is the only constructor, and this is the only, these two are the only update operations. So these are the only ones we need for well-formedness. So let's test all of our properties. So we have, firstly, the well-formedness checks. Let's try and do those. So firstly, empty, that's easy. And now we have DQ, no instance for show Q. Oh, doesn't like that. There we go. Bam, non-exhaustive patterns in function DQ. And you can see the counter example that QuickCheck gave me is, it gave me the empty Q. So I'm going to go to my editor. It's because I forgot to take into account the fact that DQ here is a partial function, which means that I also need to make sure that that the size of the Q is greater than 0. In other words, that we've got more than 0 elements in the Q. So we'll add that precondition here. And we'll also probably need that for DQ here and here. Okay, cool. So now, oh no, our properties do not seem to maintain, our program doesn't seem to maintain the data invariant. So what's going wrong? Well, the first two data invariants seem to be satisfied pretty easily. The front and the rear have their sizes kept track of in the queue, just to make looking up the length faster. And each time we dequeue an element, we subtract from the size, and each time we enqueue an element, we add to the size. But the third data invariant, that the size of the front is always greater than or equal to the size of the rear, over here, is not always preserved. In the trivial case, when I enqueue onto the rear of an empty queue, which is what QuickCheck pointed out to me, then the rear is bigger than the front. So what I'll do is I'll write a function called inv3, invariant 3, and it's going to be applied to the results of both enqueue and dequeue, inv3. And what inv3 is going to do, it takes in a queue and gives me back a queue. And what it's going to do is whatever it needs to in order to ensure that the property is maintained, that the well-formedness predicate is true. So, firstly, we've got our queue, and we check, is the size of the front greater than or equal to the size of the rear? If it is, then we're done, and we can just return the queue as is. There's nothing we need to do to fix it. But if the size has changed, and it is now not the case that the size of the front is bigger than the size of the rear, then what we'll do is reverse the rear and put it on the front, right? So we take, because remember the rear is stored in reverse order, so the front is now going to be the front plus reverse of the rear, and the size of the front is now the size of the front plus the size of the rear, and the rear is now empty. Now this looks like a slow operation. I'm sure you'll agree. This is doing a plus plus, it's doing a reverse. This could be quite slow indeed. But this order n operation here only happens every n times. And I'll show you some working that demonstrates that in a moment. But anyway, now we have our function. So this should at least satisfy our data invariance now. We make sure that the third data invariant is maintained just by fixing it if it gets broken after we enqueue or dequeue. So now, oh, it still doesn't like me. So if I enqueue onto the oh, I was breaking another data invariant here without even realizing. I forgot to add to the size of the queue when I added an element. So now, okay, cool. So now it seems to have found all of my bugs, which I wrote because of that. So dequeue is discarding about 10 tests. Those are the tests where the size of the queue is empty, right? So it is discarding some tests here, but it is still managing to pass 100, so that's good. So enqueue and dequeue both seem to maintain our data invariance, as does empty queue. So those are our well-formedness predicates. We can even check that our generator is always producing well-formed values just by doing that. So now let's check our refinement statements. So we've got these refinement statements here. Empty, size, enqueue, dequeue, front. Right. So we've got first empty. Yep. Empty is a refinement. That's good. Size. Sounds good. Enqueue. Sounds good. Dequeue. It's discarding the empty case again, but that's fine. And front. Also discarding the empty case. But it looks like we now have a completely correct implementation of a queue, and we've tested that this queue behaves the same way as our simple mental model of a list does, which is great. So yeah, so we just established these predicates. So in my slides, I did not include the precondition that the queue is well-formed because our arbitrary instance always generates well-formed queues. But I put it in my code because it's a bit clearer that way, and there's no harm in putting that extra precondition in. So we just implemented the queue, and whenever necessary, whenever we had to re-establish that third data invariant, we took the rear, reversed it, and appended it to the front, right? So this is slow. It happens. It's an order n operation, but it only happens every n operations or so. So this is what's called amortized complexity. And if you've seen this, you've probably seen this before, but if you haven't, I'll show you how it works. So we have this example here. If I enqueue the number 1 onto my empty queue, I get this. So I've run my invariant 3 function that reverses the rear and puts it on the front, and that's why the 1 is there. And that's why I have put this star. This star means I ran that reverse operation. And then it takes another enqueue before I get a chance to run that reverse operation again. And then the next time I run it, it's 4 steps that have to be taken before I can run it again. And if I kept going, so first it was 1 step, then it was 2 steps, and then it was 4 steps, the next one would be 8 steps, and then 16 steps. So because it's growing exponentially like this, the number of times I have to do this decreases, right? The times where I can safely order 1 enqueue outweigh the times where I have to do the order n enqueue by a factor equal to n, which means that overall it averages out to order 1, right? So this is amortized complexity. Okay, so there's one more example of an abstract data type that I want to show you, and that is the bag. So if you've done some of my other courses, you may have seen this abstract data type before. I like to use it in a lot of examples or in my papers as well. Essentially, we have a bag and an empty bag operation, which is our constructor, add to bag, which adds an element to the bag, and average bag, which returns the average of all the numbers in the bag. So it's just a bag of numbers, right? That's how we can conceptually think of it. So our mental model, our abstract implementation here, is going to be an empty bag, the add to bag operation an empty list is our empty bag, add to bag operation just adds to that empty list, and the average bag operation just takes the sum of all the elements in the list and then divides it by the length, right? Very straightforward. Except for when we have no elements, of course, and then we return nothing. But in our implementation, do we really need to keep track of all of this information? The only operations that our abstract data type supports is empty, add to bag, and average. Which means that the only information that I need to keep track of is the total number of numbers that I've been put into my bag and their sum. If I have those two numbers, I can just divide them to get the average, and there's nothing else that I need those numbers for. So I don't need to keep track of each and every number. I can have a more efficient implementation just by storing those two integers. So let's implement it that way. We have a record here with a total field and a count field. The empty bag is just 0, 0. Add to bag, I add to my total and I increment my count. And average bag, if I've got no numbers, I return nothing. Otherwise, I just divide the total by the count, right? Very straightforward. But how could we establish an abstraction function for quick check testing to show that this concrete implementation is a refinement of our mental model, our abstract implementation? How do we show that with quick check? The abstraction function would have to take in a bag and produce a list of integers, right? Now, it's possible to do this. We could take in our bag and construct a list of integers that averages out to the same, or that has the same total and the same number of integers as this one. But this is a little dodgy. In particular, the abstraction function just doesn't have all the information. It doesn't know exactly what numbers were added to the bag, right? So instead of using a toAbstract function, we'll have a refinement function. We'll go in the other direction. So we'll take our mental model, x's, and then we'll produce the concrete function bag, the concrete object bag that represents the implementation of our mental model, right? So we'll actually go in the opposite direction. And this is called a refinement function, right? Because it's the opposite of an abstraction function. So the way we implement our properties then is very similar to the ones with the abstraction function, except the refinement function is placed on the opposite side of the equals. So we say, take my abstract bag, convert it to a concrete implementation, and it should be equal to the empty bag. And similarly, if I add to my abstract bag an element and convert it to the concrete implementation, that should be the same as the concrete implementation of my bag with the new element added. And then average bag of the two should be equal as well, right? So this is a pretty, how should I say it? This is essentially the same structure that we saw with our abstraction function, except it's all swapped around. Now, if you look at this for long enough, you might think, well, doesn't that just mean that our abstract bag is actually our implementation, and our concrete bag is actually our specification, our abstraction? And if you look at it that way, you wouldn't be wrong. It's not entirely wrong to say that this is the implementation and this is a specification, except that this serves the purpose of our mental model. So this is our abstraction in that sense, and this is just how we choose to implement it on a computer for efficiency reasons. So I would say that a bag is conceptually a collection of integers, and so this conceptual representation is our abstract one. And our concrete implementation is just how we choose to implement it. So when you have an abstract model that actually contains more information than your concrete implementation does, then it can be helpful to use a refinement function instead of an abstraction function. Okay, but I mean, this is an uncommon case. Almost always you'll end up with an abstraction function that goes from concrete to abstract rather than from abstract to concrete. Okay, so assignment 1 has been released. So it's due right before the Wednesday lecture in week 5, and then after week 5 there is the flexibility week. So there'll be nothing on for this course at all in week 6, and all of the due dates that will come out next week in week 5 will actually be due in the first week back, which is week 7, right? So you'll get an extra week to do those things, but they won't be any more difficult. The idea is that we want week 6 to actually be a break for you. So previous students of this course have always said that these assignments that I've released, like assignment 1, it doesn't really involve much coding. You only have a handful of functions to implement, and there's not that many cases for each one. But they do involve a little bit of thinking. You do have to think carefully about how it works, and Quick Check can help you by giving you counter examples, but sometimes it can be a bit tricky to get the functions just right. So make sure you start early, so if you get stuck, you'll have time to get unstuck. So there's the homeworks as usual. Get started on assignment 1. The programming exercise is also out, and the quizzes as well. There's a new quiz for this week. And unlike previous week's quizzes, this quiz actually covers this week and last week's content. Okay, so this video is a little shorter than normal. That's okay though. I am not inclined to cover the content that I want to cover next week yet, because that's a whole new topic, and I think it would be nice to close off our examination of property-based testing with this short lecture. Okay, thank you very much.